Welcome back, everyone. Okay, so today's explainer is, well, it's a fascinating, but definitely sobering, deep dive into complex infrastructure and exactly what happens when the invisible safety nets we literally bet our lives on simply fail. We're putting the December 2025 Rohtasgarh Ropeway collapse right under the microscope. And we aren't just looking at the wreckage today. No, we're going to perform a rigorous forensic dissection of the structural and mechanical missteps that led to this massive disaster. So grab your notepad, because we are mapping out exactly where the blueprints met reality and where the safety standards fell violently short.
Okay, let's dive into this. Millions of tourists trust these systems blindly every single year, right? They're suspended hundreds of feet in the air. So obviously a ropeway trial run is supposed to be this highly controlled, tightly monitored engineering event. It's the absolute final exam before the public is allowed anywhere near the cabins. Yet this highly anticipated test at Rohtasgarh devolved into a catastrophic, multi-tower collapse. So how does a routine procedure go so terribly wrong? Was it a single point of failure or a cascade of compromised decisions?
Well, the inciting incident of this whole disaster really centers entirely on one specific pillar. Tower number 5 failed under a load test, and that immediately triggered a catastrophic chain reaction that tore down the line and completely destroyed multiple cabins. Now, when a massive steel pillar gives way, it doesn't just fall. It violently yanks thousands of feet of high-tension cable along with it, transferring unimaginable force to literally every other tower connected to the system. To understand exactly how Tower 5 fell, we have to strip away the steel and look straight down into the dirt.
So let's start with forensic layer 1, cracks in the foundation.
You know, every major infrastructure project is governed by this dense alphabet soup of international and local codes. Here we're talking about EN 1307 and IS 5228. These aren't just polite suggestions, they're incredibly strict civil engineering standards that mandate rigorous safety factors for tower foundations. And this is absolutely crucial in hilly terrains like Rohtasgarh, where soil stability isn't uniform at all. Proper adherence to these standards means you can't just pour some standard concrete and call it a day. You have to conduct site-specific geotechnical audits to ensure the ground itself can withstand the immense, twisting pressures of a fully loaded ropeway.
And this right here brilliantly illustrates where the first fatal gap occurred. Because what was missing from the equation? Dynamic load calculations. You see, a ropeway isn't a static thing. When cabins are suspended on a wire, the wind causes swing, and the sheer tension of those massive ropes creates uplift. It's literally trying to pull the tower right out of the ground. If an independent third-party audit had rigorously verified those specific dynamic load factors, the fundamental inadequacy of Tower 5's foundation would have been flagged long before a single steel cable was ever tensioned.
Which brings us to forensic layer 2, the fatal trial run and equipment failure. Trial runs are governed by really stringent commissioning standards, specifically EN 1908 and IS 5229. You absolutely do not just load up the system and hit the gas. Testing has to go through very strict, incremental phases. First, you run empty cabins just to check the baseline mechanics. Next, you load them evenly to test balanced loads. And finally, you simulate the worst-case scenarios with unbalanced loads. The Rohtasgarh collapse occurred precisely during one of these crucial, high-stress load increases.
And that leads to this seemingly simple, yet chilling catalyst of the disaster. A wire simply got stuck. Now, in a modern, standard-compliant system, a stuck wire shouldn't bring down a mountain's worth of steel. The system should be equipped with highly sensitive line force sensors. The exact millisecond that tension exceeded a safe threshold because of that snag, those sensors should have automatically triggered an immediate emergency stop, freezing the entire system in its tracks safely. But that didn't happen here.
So the really crucial question is what mechanically happens next when that tension builds up. Let's translate some of that dense engineering jargon. You need a derailment protection device, or DPD. Think of a sheave kind of like a giant bicycle gear. If the chain, or in this case, the massive steel hauling rope, slips off, the DPD acts as a specialized rope catcher. Dictated by the EN 129029 standard, properly calibrated DPDs are designed to safely catch that slipping rope, entirely preventing it from throwing massive destructive lateral loads against the tower structure.
Let's walk through how this built into an unstoppable domino effect. First, the wire snags. Second, the tension spikes way past safe limits. Third, the electronic e-stop completely fails to do its job and shut down the motors. Fourth, the physical failsafe, the DPD, fails to catch the road cable.
And finally, that runaway, catastrophic lateral force grabs hold of tower number 5, which, remember, we already know had a weakened foundation, and violently pulls the towers completely out of alignment. A localized snag instantly became a multi-tower collapse.
But the investigation goes even deeper than just the mechanics. After the dust settled, preliminary findings by IIT Patna were released, and they pointed to severe concerns regarding the actual material quality of the system. This revelation ultimately led to the contractor being completely blacklisted. But man, it raises a massive, glaring question for us. How on earth did substandard steel ever make it through the pre-commissioning quality gates to be erected on that hillside in the first place?
Well, the answer lies in exactly how materials are vetted. Under European CEN standards, specifically EN 1292/78, you can't just look at a piece of steel and declare it safe. They mandate magnetic rope testing, or MRT. This is an advanced form of non-destructive testing that utilizes ultrasound or X-rays to peer deep inside the metal itself. Strict adherence to this metallurgical certification process ensures that dangerous porous materials or faulty internal welds are caught long before they bear any human weight.
Let's pull back and look at the bigger picture. The root cause. Standards under the microscope.
Now, what's really interesting about comparing these two frameworks directly is the stark, undeniable contrast. On one side, we have the Indian BIS standards, which rely pretty heavily on general safety and installation codes. On the other side, the European CEN standards, where BIS asks for basic, kind of rudimentary interlocks, CEN demands advanced, multi-layered fail-safe systems and completely redundant sensor arrays. Where BIS allows for periodic manual inspection, CEN requires precise condition-based monitoring with strict, standardized discard criteria. Basically, one is a broad net, the other is a microscopic filter.
This high contrast juxtaposition right here is exactly why we're talking about this. Visual and functional checks might tell you if a tower looks straight today, for sure. But rigorous, non-destructive testing, MRT, and dynamic load simulation, those tell you if that tower will survive a violent storm or a sudden mechanical halt tomorrow. And that is exactly why the CEN standards are universally considered the superior benchmark for preventing large-scale infrastructure disasters.
So how do we move forward? Blueprint for prevention. A fail-safe future.
To ensure a fail-safe future, these three mandates have got to be entirely non-negotiable. First, an independent safety audit governed by EN 1709, meaning a third party mathematically verifies foundation torque and tower verticality before any load test happens. Second, integrated sensor logic. We absolutely need automation that detects a rope-stuck condition and cuts motor power in milliseconds, not minutes. And finally, strict materials certification, ensuring rigorous third-party verification of the exact yield strength of structural components like tower number 5.